Welcome viewers. In this video we'll see the energy stored in inductor and energy density of the inductor. First we'll see the energy stored in inductor. Let us consider this inductor is available. It is connected with the DC supply. It is connected through switch and the ammeter. When the DC supply is given, the current will flowing through the inductor. So due to rate of change of current, EMF is induced in the inductor. See the direction, the induced EMF is opposing the supply voltage. This opposition is converted into work done, that is nothing but energy stored. The opposition of the induced EMF by the voltage source is converted into energy stored in the inductor. Right? So an inductor is available, energized with the DC supply through the switch and ammeter. When the DC supply is given, the current will flowing through the inductor. Due to rate of change of current, EMF is induced in the inductor. That EMF will oppose the supply voltage. So the work done by the DC source against this opposition is converted into energy stored in the inductor. So the work done is equal to energy stored. So the details are given. Ammeter, this S is nothing but switch. V is the DC voltage source, E is the induced EMF, L is the inductor. So the description is available. When a DC voltage is applied to the coil, the current increases exponentially. Due to change in current, an EMF is induced in the inductor. The direction of induced EMF is such that it opposes the applied voltage in the closed loop. There is a opposition between induced EMF and applied voltage. So the work done by the DC source against the opposition is stored in the form of energy in the inductor or magnetic field. Right? So this work done is nothing but done by the DC source against the opposition, that is converted into energy. Right? So the induced EMF in the inductor. The induced EMF in the inductor is nothing but E equal to L di by dt. It's a normal general formula. E equal to L di by dt. Now dW is the work done to increase the current by I. What is the work done? Increasing the current from 0 to I. That is to the current di. So by law of conservation of energy, work done is equal to the energy stored. This work done is nothing but energy stored. Both are equal, right? So this is the EMF induced. In this, the energy stored is nothing but to need to increase the current by the dI value. So that the increasing the current is the energy stored, that is equal to the work done. Now we'll see what is the work done. So the energy is given as power into time. The general formula for energy is nothing but power multiplied by time. This energy is equal to the work done. Just now we discussed the work done is equal to the energy. So the energy is represented as dW, work done. This dW represents the work done by small current. By integrating we will get the total work done. So the power is nothing but voltage into current, EMF induced into current, into time is dt. Right? This EMF induced in the inductor is L di by dt. Just now we discussed this formula, L di by dt into I into dt. So this dt got cancelled. So what we have? dW equal to Li into di. Right? So this is the work done due to the small current di. Work done, dW means small work done by the small current. So the total work done to establish the current of I can be obtained by integration. So by integrating on both the side with a limit, we can get the total work done. So integral dW equal to integral Li into di. What is the limit? The work done is nothing but increasing the current from 0 to maximum value of current I. So the limit is from 0 to I. The work done is nothing but increasing the current from 0 to I. Now we'll go for this integration. So integral dW equal to W, that is equal to this L is constant. Only we need to integrate 0 to I into di. We need to integrate only I. So W equal to L. This integral I is nothing but I square by 2. Right? Integral of I is I square by 2. We need to substitute the limit 0 to I. So W equal to L, substitute the upper limit I square by 2 minus lower limit is 0. So that W equal to L I square by 2. So that can be written as W equal to half L I square. So that is the energy stored in the inductor. W equal to half L I square. So this I represents the energy stored in inductor, means current is increasing gradually or current is decreasing gradually. The charging, the inductor is storing the energy or discharging the energy, means current increases or decreases gradually. In case of capacitor, the work done is nothing but half CV square. The voltage in capacitor, charging and discharging, means the voltage is increasing or decreasing gradually, right? So the inductor W, energy stored, equal to half Li square. Now we'll see the energy density of the inductor. Now we'll see energy density. So the energy density is nothing but energy stored per unit volume. So the density means always we can refer either length, area or volume. Here we are referring volume, right? Density, how much density for a given volume, right? So the energy density is energy stored per unit volume. So for that, first we'll start with the energy stored. Energy stored in the inductor. Energy stored in the inductor is half Li square. Just now we discussed half Li square. In this, what is the inductor? Inductor value, general formula n pi by I. Now we'll substitute this L, replace this L with n pi by I. Therefore, energy stored equal to half Li square. L is nothing but n pi by I into I square. So 1 I got cancelled. So half n pi into I, right? So the energy stored is half Li square. In this, L is replaced by n pi by I. At the time 1 I got cancelled, we got half n pi into I. In order to get the volume, we are going to multiply and divide by the term length L, right? We are going to multiply this expression and divide by the length L. So that energy stored equal to half n pi by I into L divided by L. So while multiplying and dividing, the originality will not change. Now rewrite this 1 by 2. This n into L is written separately, n into L. Remaining pi I divided by L is rearranged, right? N into L is written here, pi I divided by L is written here. So n into L is nothing but number of turns into length is nothing but a volume, right? So that is written as pi I divided by 2L into volume. Number of turns multiplied by length is nothing but a volume, right? So now we can see that. Now bring this volume in the denominator, this left hand side. Energy stored by volume equal to pi I divided by 2L, right? This volume is brought in the denominator. What is energy stored by volume? Is nothing but energy density. Energy stored by volume is the energy density, that is equal to pi I divided by 2L. The unit is joules per meter cube, because it is divided by volume, it is meter cube, joules per meter cube, right? So the energy stored in the inductor is nothing but pi I divided by 2L, joules per meter cube. Now we'll see the energy density of the solenoid. So the energy stored in the energy density of the solenoid, right? And this energy density is nothing but energy stored per unit volume. So first we will refer the energy stored in the inductor. Energy stored equal to half Li square. In that, what is the inductor value? The previous derivation we refer the general formula L equal to n pi by I. Here we are referring inductor of a solenoid, right? Because we are going to find energy density of the solenoid, right? So the inductor of the solenoid is nothing but mu n square A by L, right? We need to replace this inductor expression with inductor of a solenoid, mu n square A by L. So that energy stored equal to half Li square. L is nothing but mu n square A by L into I square. right? So in order to get the volume, here also we are going to multiply and divide by the length L, right? Multiplied and divide by the length L. So that energy stored equal to half, that is mu n square A divided by 2L into I square divided by L into L, right? We are going to multiply and divide by the term L. Now rewrite this mu n square divided by 2L into I square. A into L is written separately, right? A into L, area into length. Remaining terms are written here. Mu n square, this I square divided by 2L. Here 2L is available. L, here one more L is available. L square. A into L is rewritten. What is area into length? Area into length is nothing but volume. Area refers two parameters into one more parameter. Three parameters means it is a volume, right? Breadth into height, we can refer breadth into height in the area. Into length, length, breadth, height means it is a volume, right? Now energy stored equal to mu n square I square divided by 2L square into volume, right? Now bring this volume in the denominator. This volume is brought into denominator. So energy stored by volume is nothing but energy density. That is mu n square I square divided by 2L square, right? This is L square. Joules per meter cube, right? So this is the expression for energy stored in the solenoid. Previous one is the energy stored in inductor in general. This is specifically for a solenoid, right? Now we'll see one problem based on the solenoid. So in this problem, a solenoid with 200 turns, the number of turns equal to 200, 3 millimeter long. The length of the solenoid is 3 millimeter, that is 300 into 10 to the power minus 3 meter, right? The millimeter is converted into meter. And 20 millimeter in diameter, right? The diameter is 20 millimeter, then radius will be 10 millimeter. That is converted into meter. 10 into 10 to the power minus 3 meter, right? The number of turns available, length is available, diameter available. From that we calculated radius. The current is 600 milliampere. 600 into 10 to the power minus 3 ampere. Milliampere means we need to multiply with 10 to the power minus 3, right? What is then? We have the constant mu naught equal to 4 pi into 10 to the power minus 7, right? What we need to calculate? We need to calculate inductance of this solenoid and energy stored in the solenoid, right? Energy stored as well as inductance value. We'll find this one by one. So the inductance of the solenoid is L equal to n square mu A by L. Inductance of a solenoid is, just now we discussed about that, n square mu A by L, right? This A is nothing but pi r square because we are having the radius available, so the area is nothing but pi r square. So n square mu pi r square divided by L. Now we'll substitute all the values. The number of turns is 200, 200 square into mu. Mu is nothing but mu naught. Mu r value is 1. So mu naught is 4 pi into 10 to the power minus 7 into pi r square. Pi into r square. R is nothing but 10 into 10 to the power minus 3 square divided by L. Length is nothing but 300 millimeter. That is 300 into 10 to the power minus 3. Now all the values are substituted. By simplifying this, what we got? 5.263 into 10 to the power minus 5. The unit is Henry. So the inductance of the solenoid is 5.263 into 10 to the power minus 5 Henry. Right? Now we'll find the energy stored in solenoid. Energy stored. What is the formula for energy stored in general? Half Li square. Right? We got the derivation half Li square. So half into L. L is nothing but just now we calculated 5.263 into 10 to the power minus 5 into I square. I is 600 milliampere. So 600 into 10 to the power minus 3 square. Right? So by simplifying this, what we got? 9.4 into 10 to the power minus 6 joule. Right? The energy stored is given in joules. So 9.4 into 10 to the power minus 6 joules, right? So now we calculated inductance of the solenoid, energy stored in the solenoid. So in this video we discuss about energy stored in inductor or magnetic field, then energy density of the inductor, then energy density of the solenoid. Based on that we discussed one problem based on the solenoid, the inductor value as well as energy stored in solenoid. Thank you.